A layer of coarse wool covered in dust and fleas on a sheep's back can eventually become the fabric used in some of the world's most luxurious suits that can sell for more than $10,000. But how is this rough material transformed into something so soft, durable, and valuable? The journey begins on vast farms, where sheep are carefully raised, inspected, and shorn with precise movements. The raw wool is then sorted, washed, dyed, and blended before millions of individual fibers are carded, combed, and spun into long, fine, and uniform yarns. Finally, the warp and weft threads are interlaced on high-speed looms to create unfinished wool fabric, which then undergoes washing, steaming, raising, shearing, and surface setting. In this episode, Factron Process takes you inside the complete production line for premium wool, following its transformation from fleece on a sheep's back into finished rolls of fabric used in luxury fashion products around the world. Since prehistoric times, humans have learned to transform sheep's wool into yarn, fabric, and felt. Over thousands of years, this material has appeared in the tents of nomadic peoples, military uniforms, woven carpets, royal garments, and eventually in suits regarded as symbols of power and refinement. Hidden within the coarse fleece covering a sheep's back is one of the most sophisticated natural materials ever used by humankind. Each wool fiber is made of keratin, the same protein found in human hair and fingernails. Yet superfine merino wool can measure only around 17.5 micrometers in diameter. Its unique structure allows the fiber to absorb moisture equal to as much as 35% of its own weight before the surface begins to feel wet. On average, a single sheep produces around 4.5 kilograms of wool each year, enough to make more than 10 meters of fabric. Over 1 billion sheep supply nearly 2 billion kilograms of raw wool. Yet wool still accounts for only around 1.2% of the global supply of virgin textile fibers. At the extreme end of rarity, one batch of ultrafine wool measuring just 13.8 micrometers once sold for a record 10,300 Australian dollars per kilogram. The journey of producing a premium wool fabric begins across the vast grasslands of the northern tablelands in New South Wales, Australia. At Balala Station, a farm covering approximately 1,215 hectares, merino sheep are raised to produce ultrafine wool with an average fiber diameter of just 16.5 microns. From the breeding stage, farmers prioritize healthy animals that produce long, uniform fibers and adapt well to the local climate. The flock is divided according to age, physical condition, and reproductive stage. Each group is rotated between grazing paddocks, allowing the pasture time to recover while preventing the sheep from grazing too close to the ground, where parasite larvae are often concentrated. Farm managers regularly assess grass density, water availability, and the body condition of each flock before deciding when to move them to the next grazing area. Nutrition directly affects the growth rate, strength, and quality of wool fibers. In addition to natural pasture, pregnant ewes, nursing sheep, and animals in poor condition receive supplementary feed rich in energy, protein, and minerals. With an average annual rainfall of around 795 millimeters in this region, pastures generally grow well, but farms still maintain feed reserves to prepare for dry seasons and periods of unfavorable weather. To eliminate lice, ticks, and other parasites hidden deep within the fleece, the sheep are guided through a dipping bath containing a specialized parasiticide solution, often formulated with active ingredients such as diazinon. The head is submerged only briefly once or twice, and lifted immediately, so the sheep will not suffocate when the procedure is performed correctly. The main advantage of this method is that the solution can penetrate the thick fleece and reach the skin, providing more even and effective treatment than simply spraying the outer surface. Merino sheep are typically shorn once a year during spring, when weather conditions are relatively stable, reducing the risk of the animals being exposed to cold rain immediately after losing their natural protective fleece. On the shearing floor, the shearer gently holds the sheep in a seated position, supported against his legs. This technique limits struggling, without the need to restrain the animal with ropes. Electric shears use a fixed comb and a rapidly reciprocating cutter, which glide close to the skin and remove the fleece in broad strips. The process usually begins at the belly, where the wool is shorter, dirtier, and less valuable, so it is collected separately. The shearer then works around the hind legs, tail, and groin, before making long, continuous blows from the rump along the body toward the shoulders, neck, and front legs. Sheep are usually kept in holding yards and withheld from feed and water for at least around 8 hours. This reduces the weight of the digestive system and helps the animal remain more comfortable as the shearer changes its position. A typical Merino ewe can produce approximately 3 to 6 kilograms of wool in a year. The freshly removed fleece is spread across a mesh sorting table, where stained edges, belly wool, and lower quality fibers are removed before grading. After shearing, the sheep's skin is inspected and the animals are quickly given access to food and water, while being protected from wind, rain, and low temperatures. In a single operation, the natural coat that has taken nearly a year to grow is removed almost intact, marking the beginning of its transformation into premium merino wool fabric. The freshly shorn fleece is thrown onto a mesh sorting table and spread out completely, allowing loose dirt and short fiber fragments to fall through the openings. The workers manually remove belly wool, stained edges, matted sections, discolored fibers, and areas containing excessive impurities. They then use their eyes and hands to assess the wool's fineness, length, color, softness, and strength. For Australian superfine wool certified under the 1pp standard, fiber diameter must not exceed 16.9 microns, while vegetable matter must remain below 1%. Only wool sections with similar characteristics are grouped together, ensuring a consistent batch before baling and transportation to the processing mill. At the raw material processing area, the wool bales are opened, blended, and spread into an even layer so the material can move steadily through the production line. At this stage, greasy wool may still contain wool grease, dried perspiration salts, soil, and sand amounting to around 35 to 40% of its total weight, leaving the fiber clumps heavy, oily, and difficult to process. The wool then passes continuously through a system of approximately 6 to 8 scouring bowls. The first bowls use warm water mixed with a mild detergent, sometimes with a suitable alkaline agent, to dissolve perspiration salts and emulsify the grease coating the fibers. The following bowls contain clean water to rinse away the dirty solution and any remaining chemicals. Between each bowl, pairs of squeeze rollers press out grease-laden water and dirt without crushing or damaging the wool fibers. The separated grease is recovered from the wastewater and refined into lanolin for use in cosmetics and a wide range of personal care products. The cleaned wool then enters a continuous dryer or rotary drum dryer, where heated air is distributed evenly through the fiber clumps. Temperature and residence time must be carefully controlled, because excessive drying can make the fibers brittle, while overly vigorous agitation can cause the surface scales to interlock and produce felting shrinkage. After drying, the wool is opened again to remove additional sand and insoluble dust, then placed in an enclosed conditioning chamber to equalize its moisture content. Modern scouring lines deliberately leave around 0.3 to 0.5% residual wool grease, as this extremely thin coating acts as a natural lubricant, reducing friction and limiting fiber breakage during the next carding stage. Finally, the wool is compressed into bales, weighed, and labeled with identification codes before being transported to the spinning mill. In fully integrated facilities, however, the material may move directly into carding or combing without being baled in between. After being thoroughly washed and dried, the wool is transferred to the dyeing stage in loose fiber form. In an acid dyeing process, the solution is usually adjusted to a pH of 4 to 5, then gradually heated to around 95 degrees Celsius so the dye can penetrate deeply and bond evenly with the keratin proteins in the fibers. The wool remains in the dye bath for approximately 30 to 45 minutes, depending on the type of dye and the required shade depth. If the temperature rises too quickly or the fibers are agitated too aggressively, the wool may felt and lose strength. At the end of the cycle, the wool is rinsed to remove excess dye, then pressed or centrifuged to extract most of the water. The material is opened again, spread evenly across a conveyor, and dried for a second time using a circulating stream of heated air. After drying, the wool is cooled, conditioned to equalize its moisture content, and inspected for color consistency before moving on to blending, carding, and spinning. Once the wool has reached a stable moisture level, the fiber bundles are weighed according to the required proportions and fed into the blending system. Batches differing in color, fineness, and origin are opened and mixed thoroughly to break apart fiber clumps formed during drying. At this stage, the cleaned wool still retains around 0.3 to 0.5% natural grease, which acts as a lubricant to reduce friction and limit fiber breakage. A very fine mist is then introduced to control static electricity and restore flexibility. Because wool can absorb moisture equal to around 35% of its own weight before feeling wet, the fibers gradually regain their natural loft, softness, and elasticity. The uniform blend is then transferred directly to the carding machine. The blended wool is fed evenly into the carding machine, where a series of cylinders covered with fine steel teeth rotate in different directions and at different speeds. These precisely controlled movements open each fiber clump, untangle the wool, and remove any remaining dust or impurities. In the woolen system, the fiber web leaving the first carding section is turned 90 degrees before entering the second, improving the uniformity of color and weight across its entire width. By the end of the line, the loose wool has been transformed into a fine, continuous web and divided into soft strands ready for spinning. This stage plays a decisive role in determining the evenness, softness, and smooth finish of the final yarn. The softly carded wool slivers are transferred to the combing machine, where rows of fine steel pins continuously separate and align the fibers. Long fibers are retained, while short fibers known as noils, along with knots and any remaining impurities, are removed from the material stream. For exceptionally fine wool, the process may be performed twice to achieve even greater cleanliness and uniformity. By the end of this stage, the long fibers lie almost parallel, producing a continuous wool top with a smooth, lustrous, and highly consistent structure. This refined material forms the foundation of fine, strong, and low-fuzz worsted yarns used in luxury suits, coats, and other premium wool garments. Leaving the combing machine, the wool top is clean and parallel but still too thick to become yarn. It first passes through drawing and roving machines, where it is gradually reduced in thickness by around 40 times to form a light, uniform roving. Even a small variation at this stage could later become thousands of meters of uneven yarn. The roving then enters the drafting zone of a ring spinning machine. Successive rollers rotate at increasing speeds, drawing the strand to roughly 20 times its original length, while keeping the fibers overlapped and connected. Rapidly rotating spindles then insert hundreds of twists into every meter, locking the loose fibers into a strong, elastic structure. Too much twist makes the yarn firm. Too little leaves it weak and prone to fuzzing. So tension and twist must be carefully balanced. The yarn is wound onto bobbins and inspected by electronic sensors for thick places, thin places, knots, and other irregularities. Faulty sections are removed, and the ends are rejoined with compressed air to create a fine, nearly invisible splice. Premium yarns may then be twisted into two-ply constructions for greater strength and stability. The result is a fine, smooth, lustrous worsted yarn, soft enough for luxury suiting, yet strong enough to withstand weaving and finishing. The finished wool yarn is transferred to the weaving section, where thousands of individual threads are interlaced to form a complete fabric. Before production begins, sensors check the moisture level, tension, and uniformity of each yarn batch to prevent streaks or structural defects from appearing across the surface. The warp yarns are arranged on a beam and threaded precisely through each heddle eye and reed dent according to the weaving pattern. Automatic drawing-in machines can process up to 170 yarn ends per minute. During weaving, the heddle frames rise and fall continuously. Rapier grippers carry the weft yarn across the loom, and the reed beats each insertion firmly into place to create the required density and pattern. Some high-speed rapier looms can operate at around 750 revolutions per minute. Electronic sensors immediately stop the machine if they detect a broken yarn, abnormal tension, or an irregular weave. Finally, the fabric is wound onto a large roll, inspected under bright lights, and repaired by hand before proceeding to washing, softening, shaping, and surface finishing. The raw wool fabric enters wet finishing, where controlled washing and milling consolidate its structure, remove processing residues, and improve its handle. Fine rollers then raise and shear the surface, while selected fabrics may be dyed and steamed to stabilize their color and dimensions. In advanced continuous decatasizing, the cloth can be treated at around 135 degrees Celsius under pressure. Final drying and moisture conditioning give the fabric its softness, resilience, smooth surface, and natural luster.